Last episode, you hit the ceiling of a hand-rolled loop, a while block, a scratchpad string, and no way to see the shape of what your agent did. Today, you stop describing the loop and start declaring it. You build your first state graph, a typed state, 2 nodes, 1 edge, and the thing that runs is the same thing you draw. Here is the loop from last episode, a while block calling the model, appending to a scratchpad, deciding whether to continue. It works, but it's invisible. There is no object you can point at and say, that's my agent. The structure lives only in your head. LangGraph flips this. You define a state, a typed dictionary, the single thing every node reads and writes. Then you declare nodes, think, which calls the model, and act, which runs the tool. Each node is just a function that takes the state and returns an update to it. You wire them with edges. Start flows into think flows into act flows to end, one straight line. You call compile, and now you hold a graph object, not a description of a loop, the loop itself as data. When you invoke it, the state walks the edges. Think writes the model's plan into the state. Act reads that plan, runs the tool, writes the answer. Same state, threaded node to node. And because it's a graph, you can draw it, the exact nodes and edges that just ran. Here's the program. We import our harness, scripted LLM for the can turns, the scripted calc tool over an in-memory world, plus state graph, start, end, and an in-memory saver from LangGraph. First cell pins the versions onto the editor card. We declare the agent state, 3 typed keys, question, plan, and answer. This typed dict is the contract. Every node receives the whole state and returns a partial update. LangGraph merges it back in. The think node, it pulls the next scripted model turn, whose calc 2 plus 2, and writes it to state point top plan. We log the step into our trace. The model's words are the only fake part. The node, the state, the merge are the real API. The act node reads plan, calls the scripted calc tool over the world dict, and writes the result into state answer. Then we build the graph, add both nodes, add edges, start to think to act to end, and compile with the in-memory saver checkpointer. We invoke with the question and a thread ID, printing the state after each step. Watch the terminal, question in, plan written by think, answer written by act, 2 state transitions exactly matching the 2 nodes. Then the discipline. Reproduce runs the whole graph twice in process and asserts the 2 traces are byte identical. Assert identity checks the figure's node count, the terminal's node count, and the headline all agree, 4 graph stops. The payoff? Your agent is now an object you can run and draw. Same graph, no gap between behavior and diagram. But notice the state just got overwritten each step. Next episode, what happens when 2 nodes write the same key, reduces, and the right heat map that shows you exactly where state lands.